All right, so now that we have a chance to kind of get our hands dirty with exploring this particular statement, what I want to do is I want to step back and actually try to show this thing using mathematical induction. So in this case, if you look at this overall statement, what I'm going to see is I'm going to have this bit that's going to say for each natural number n. So it's going to be this for all n. It's not true just for a collection of n's. This is properly any n that I'd ever want to see. What's going to happen after that is that there's going to be this big kind of a bit that's going to be that big summation thing that I'm trying to show. Typically, we're going to identify this thing as being some predicate p of n. The idea here is that for various levels n, this thing should be true. So it's not a statement on its own because it's dependent upon the value n, but you can see that I've actually quantified this thing with this nice universal quantifier of for all natural numbers n. So if you really wanted to make this thing look shorthand, you'd see for all n in the natural numbers, I'm going to have some random statement p of n actually occur. So to kind of see how this predicate notation works, how it works, we can look at a few cases. So if I look at p of 1, so if I plug 1 into the left-hand side, maybe I'll make that kind of a bit more clear. I'm going to have a left-hand side and a right-hand side. So plugging in 1 into the left-hand side, well, n is then going to be the value 1. So what this thing is going to be a sum from 1 up to 1, which in this case would just be the number 1. What's going to happen on the right-hand side is I'm going to have a 1 multiplied by a 1 plus 1 all over 2, which is going to be a 2 over 2, which fires off a 1. So it's actually true at that level. Okay, let's look at a couple other ones just to kind of see what's happening, because sometimes students are really good about that one, but then the second one becomes kind of funky. What's going to happen here is that I'm going to look at a sum from 1 up to the value of n, which in this case my n is a 2, so it simply just becomes 1 plus 2, i.e. a 3. On the right-hand side, I'm then going to have n, which is a 2. So I'm going to have 2 multiplied by a 2 plus 1 all over 2. The top part becomes that 6 that we saw earlier, which we needed to divide by 2 to bring it then back to the level of 3, which it does work in that case. Likewise, if I look at P3, what that's going to be is it's going to be a 1 plus a 2 plus a 3, which we know is a 6. And then plugging 3 into the right-hand side, it's 3, and then a 3 plus 1 all over 2. This is going to be my 4. My 4 times 3 is going to make a 12. 12 divided by 2 is going to make my 6, which is exactly what I wanted to see. So what's going to happen as we run through all of this is I'm going to try to use my previous stage. The idea is that if I wanted to show P4, what's going to happen is that there's going to be a 1 plus a 2 plus a 3 plus a 4. Well, what's going to happen is that those first little pieces from 1 to 3, well, what's going to happen is that I can use this random structure that I had before and then actually try to just add 1 to it. So what's going to happen is that those first little things, they're going to turn into this value of 3 times the 3 plus a 1 over a 2. And then what I'm going to do in this case is that I'm going to add a 4 to it. So if you do a little bit of kind of math magic in this case, basically giving this thing a common denominator, what's going to happen is that I get a 3 and then a 3 plus a 1 over a 2. That 4 I can actually view then as a 2 multiplied by a 4 all over a 2. And if you look at this left-hand part a little bit more carefully, that 3 plus 1 turns into a 4, so I can actually factor a 4 out of that. So I get a 4 and then 3 plus a 2 all over 2, which is very nicely that 4 multiplied by the 5 over a 2, which is what it's supposed to be. So it's kind of a silly way to see all this stuff come into play, but that's the idea that's going to come when I try to show general k to k plus 1. So it looks weird when you go from 3 to 4 because you know what those numbers are supposed to be. But again, what's going to be happening is that this is supposed to be true for any natural number n. So what I want to do is I want to leave that very general. I'm going to call this a k, and I'm going to try to go from k to some level k plus 1 as we try to see all of these details come into play. Okay, so the general idea in all of this is going to be I'm going to assume this is going to be true for some level pk. Well, level pk is then going to say 1 plus 2 plus 3 all the way up to level k is then supposed to be k multiplied by a k plus 1 over a 2. So that's what I get to assume. I'm kind of sitting here at level 1000 and I'm now trying to go to 1000 plus 1. Or if I'm sitting at level 1,000,000, I'm then going to try to go to 1,000,000 plus 1. So in general, what I want to show, which I sometimes abbreviate as WTS, is that I want to show level pk plus 1 is true. Which is that I want to show that 1 plus 2 plus 3 all the way up to k and then a little bit more, so there's one extra term in that case, I want to show that this is in fact equal to, well, what happens to the right-hand side when I plug in k plus 1? That little n becomes a k plus 1. And then if I plug in k plus 1 into that thing, it's going to be k plus 1 plus 1, which is actually a k plus 2 all over a 2. So that's going to be my goal to get to this particular stage. That's kind of my big goal. So if I put my pk plus 1 up here, it'll make my life a little bit easier. Okay, so that's my kind of game plan, is that I want to make that blue part true. What I get to assume is I get to assume that that red stuff is actually true. And if you look at that, there's actually a little bit of connection between the blue stuff and the red stuff, just like there was a connection between the P4 and the P3, in that those first three terms actually came from the previous level. So I'm going to do more or less the exact same thing here. I'm going to start with 1 plus 2 plus 3 all the way up to a k, and then a little bit more, which is a k plus 1. So I can't say that this is equal right here because this is what I want to show. So I'm going to try to do something else to actually make that connection. What that something else is going to be using the previous level, which is that level pk, which I get to assume right now is true. It's the idea that I've climbed up to level 100. I now get to assume level 100 is true because I've made it there, and now I need to use that information to go to level 101. So what you can see in this case is that these first little pieces are exactly those first little pieces here. So I can actually swap out that number from 1 up to k with the actual bit that it's going to be. This k and then a k plus 1 all over a 2. And then I still have that extra random little k plus 1 afterwards. So I take that big summation, and then it becomes that part right there. So I try to keep these things somewhat color coordinated. The idea is that what I'm trying to show is going to be represented in blue. My actual assumption is going to be this pk, which is I'm typically going to write in red. And even once you go back and see these things typed out, I'm going to try to keep that somewhat consistent as well. So you know where things are going to be placed and plugged, and there's a little bit of kind of looping around on some of these things. So once you've done that, the second part is actually simply just going to be to take this idea here and then do a little bit of algebra to clean it up. So just in that, like that kind of silly previous example, what I want to do is I want to find some common denominator, which in this case is a 2. And then just like before, I have a k plus 1 and a k plus 1, so I can factor out a k plus 1. And then what's left over is there's going to be a k. And then there's going to be a 2, which is all over a 2, which is exactly what I wanted to see. So the idea is that I can compute all of that, and everything cleans itself up pretty nicely. And I found out that my battery is running relatively low. So we'll have to cruise through this thing so we can see some of these arguments come into play. But the idea is that you're always going to take these things, literally copy and paste the argumentation around it, and then just do up a little bit of algebra in the middle. So sometimes students get a little bit hung up in the actual algebra part in the middle, but that's not supposed to be the part where you get kind of scared or anything like that, because that's the relatively kind of just, I don't know, algebra 2 or algebra 1 side of things, but there's a little bit of factorization that ends up happening. But what's nice about it is that you know exactly where you're supposed to go. So if you were to, at least in this case, let's say multiply out the entire top part, you would have seen a k squared plus a k, and then the other part would have been a 2k plus a 2, all over a 2. And then if you would have combined these things, you would have seen a k squared plus a 3k plus a 2, all over a 2. And then if you stare at that thing and you're like, oh man, now I have to factor this thing, well, look at where you're trying to go. You know where you want to be. And the idea is that, okay, it's supposed to be a k plus 1 times a k plus 2. If you FOIL that whole thing out, boom, you're right back to k squared plus 3k plus 2. So you do have this very nice check to kind of see what's actually happening in this process. If you're actually doing it correctly, you should get right back to where you're supposed to be. So what you can do in all this is that you can then step back and actually try to clean this up a little bit. So this is the notes you'll see in the filled out side of things. But if you're actually trying to write up one of these nice little mathematical induction arguments, there's those two key steps that are going to come into play. The first of which is going to be my basis step. That's that getting on the ladder stage. So if you plug in 1 into the left-hand side and 1 into the right-hand side, both things fire off being a 1, which actually shows that that level P1 is actually true. So then the inductive step is exactly that climbing from ladder rung to ladder rung. I get to assume level K is true, so PK is true, and then I'm going to try to show that the next level, PK plus 1, is true. So here I'm going to just let K be some natural number and assume PK is true. So here I've written PK in red, so it's hopefully the exact same as what we had in that previous slide. So that's that little bit that I get to assume. My goal is then going to be to take that red stuff and try to show the next level is true. This pk plus 1 is true. Well, if you look at that formula and plug pk, if you plug k plus 1 into it, what's going to happen is that the n's turn into k plus 1's, and you can see that that right-hand side turns into a pretty nice thing as well. It's now going to be a k plus 1 multiplied by a k plus 2. And I sometimes am extra explicit on the left-hand side is that I'll go 1, 2, 3, I'll write the k in and then have another k plus 1. So it's replacing the n with a k plus 1, but realize that there was a k in front of the k plus 1, just like there'd be a 99 in front of 100. So after that, it's going to be my goal to show this. That's my goal. So I don't get to assume it right now, but that's where I'm going to be trying to work towards. Well, what ends up happening is that if you look at the left-hand side of that goal and then break off those first k pieces, use the inductive hypothesis. So that's exactly what this red part is referred to as, is this is the part that I get to assume in this inductive step. If you realize this is a nice conditional bit. If pk is true, then pk plus 1 is true. So there's a conditional part, and that's going to have its own little hypothesis in it. So that part in red is going to be referred to as the inductive hypothesis, which is often abbreviated with an IH. So I'm using that exactly at this stage. That part in red is this part in red. They are equal by this inductive hypothesis. And then you just simply do the algebra to clean these things up, and boom, you got to exactly where I'm trying to go towards. And that finishes off the argument, basically. You can add in one extra little line that says, okay, by the principle of mathematical induction, everything is great, have a little dance, and say, yay, everything works out perfectly. As you work through some of these various summation formulas, you're going to realize that my proofs are actually all the exact same, except for I've just simply changed the algebra part in the middle, which is one of the really nice things about induction, is that the actual argumentation for these things essentially becomes a cookbook. It's kind of the Mad Libs of proof writing in this case, is that what you're going to do is let Pn be random statement, insert Pn statement. Basis step, P1 is true, realize that blah 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 happens. Okay, inductive hypothesis, insert pk, what do I want to show? Pk plus 1, insert algebra to show the connection, conclusion at the very end. And as we go through, you'll see the exact same process come into play. So these slides you can see right here are going to be a little bit of kind of the formality of what all of the kind of notation that I kind of glossed over as I was running through these things. The general idea of a proof by induction is going to have a basis step, that getting on the ladder stage. There's going to be an inductive step, going from rung to rung. What's going to happen down here is that technically there's mathematical induction, but has an extended principle, this idea that you can start anywhere you want to. I tend to just lump these things into the same camp. The idea is that I can start at 1, I can start at 0, I can start at 5,000. Wherever I need to start, just start at that particular stage. You're going to see that come into play a little bit later when I start looking at some inequalities between some, exponents and factorials, that some of these processes are only going to start at level 4 or level 7 or something like that. So just basically start where you're supposed to start. And then if you want the kind of cookbook template, that's exactly it. You're going to say, I'm going to try to show something, show the basis, show the inductive, do the algebra, clean things up afterwards.